Good afternoon. It's a pleasure to be here to present the results that we have in the last year and also to present a new topic for us that is a project that we are beginning. The title of the presentation is the title of the project that we have. It is a 4-year project which is funded by Petrobras. So Petrobras is putting two teams of our chair, that is robust optimization and geomechanics, together to do the optimal reservoir management incorporating geomechanics. Just for those that don't know where Recife is, I am at Federal University of Pernambuco, and the main campus of our university is in Recife, the capital of the state of Pernambuco. And okay, it's a big university in the country, and also it is sorry. And well, it's a very touristic city with Portuguese and Dutch colonization. So if you have a chance to go there, and also we are there in Recife. We have in our main campus. We are at the LITPEG, that is the Petroleum and Energy Research Institute, that aims to integrate industry, academia to develop new technology, promote innovation, and prepare human resource for various areas of the production, oil and gas production chain, and biofuels, and also renewable energies. And the research areas we have many research areas, and the chair is based on the geology, geomechanics, and reservoir simulation groups. We have there labs and offices for these disciplines. And regarding the chair, the title of the chair is Reservoir Modeling and Robust Optimization. And reservoir modeling means for us outcrop characterization, upscaling. So you have geologists in our team, geomechanics, carbonate and CO2 geochemistry, laboratory testing, and constitutive modeling. And for robust optimization, we understand it's more applied to WOG optimization, uncertainty modeling, machine learning, and reservoir simulation. So the proposed research can be applied for both EOR, that is related to pre-salts challenges, and also CCS projects, as we are beginning to have our first CCS projects. Regarding the strategy. Well, Andrew just mentioned that we are still increasing our oil production. We have new frontiers for the pre-salt is below, so you have new frontiers for oil. And we have a peculiar situation in terms of emissions. In Brazil, the Brazilian government is leading the ecological transformation. That is, for them, is a little bit more than energy transition. It includes also quality of life, environment. So, Brazil, the oil and gas is not the #1 industry in Brazil. Agriculture is the #1. So, for instance, the emissions that we have is much more higher in terms of land use and deforestation. So you have different scenarios. On the other hand, you have a lot of investments on hydroelectric, alcohol in our cars. So our cars can receive 100% of our cars can receive any proportion of ethanol or gasoline. So this is something that we have for many years, at least 4 decades. So, in the area that we are, in northeast part of Brazil, we have very good opportunities in terms of renewable energies. We have huge investments in solar and wind energy generation. So potentially you can have hydrogen, green hydrogen, and also we have onshore salt layers that can be used for caverns, for instance. And we have also depleted onshore oil and gas reservoirs for CCS and other kind of projects related to energy transition. So this is more or less the scenarios that you have in Brazil. And for sure, our share will be is related to energy transition, and also oil production. And this is the proposal for the new chair that we have for the next term of the chair. It's under evaluation. But I would like to give a few idea of the projects that we have for the next 3 years. So we have 2 CCS projects. One CCS project with Repsol Sinopec. That is, we have two reservoirs on sandstone and a depleted reservoir in aquifer to study. And with Petrobras, we have a CCS in Swap complex, industrial complex, that is 40 kilometers from Recife. So we have there refinery. We have a high concentration production of CO2. So this is more engineering project, and this is a more geological characterization project. And with Petrobras and Braskem, we have a project in salt caverns in the geomechanical aspects of salt caverns in a site that we have 250 kilometers from Recife in another city. And we have also, this is the project that we have related to energy transition. And we have other projects related to the pre-salts challenges. And what I'm going to present is this, What I'm going to present is this one, that is the optimal geomechanical management, but we have other smaller projects as well. So in the intersections, in the intersection of these 2 projects, we have the geomechanical risks and the monitoring. So we have sites such as the Salt Geomechanics project that we have monitoring, and we are going to evaluate geomechanical risks. Also, we are going to evaluate geomechanical risks for CCS projects. This one with Repsol Sinopec Brazil. And also, in this project that I'm going to present today, the new element that we have is that Petrobras and other companies also are doing in the pre-salt. They are putting points that can measure the deformation, the displacements of the seabed in the pre-salt area. So the idea is to include geomechanical variables in the management as this data will be generated during the reservoir production. So it's a huge opportunity because we can improve our management, but also for geomechanics, because geomechanics data is not very is scarce. So we need this data to validate our models. So it's really in a scale that we have huge scale, a reservoir scale that is related to pre-salt. So we have here, so the challenge that Petrobras put us was to join 2 groups, coupled reservoir geomechanics and robust well optimization. So the 2 groups that we have in our chair. Bernardo Horowitz is with us and leading this robust well optimization since the beginning of the chair. And we are doing, now it's a very interesting opportunity. So I will give you the initial assumptions. It can change during the project, but it's part of our discussion, internal discussion, and also discussions with Petrobras. And also I will give you some previous results that give the elements for these initial assumptions, okay? So initially, we know that we think that geomechanical proxy is expensive and challenging because of the non-linearities of and that we call low localization. So if you have fracture, classification, fault reactivation, it's too localized in the domain. So it's very hard to train a neural network or train a proxy that will capture the essential mechanism that is occurring in the huge domain that is the domain of geomechanics. So this is a point. So we are not use a black box geomechanical model to have a proxy. We are trying to simplify the geomechanics as possible. So the geomechanics, to perform the optimization, of course, the objective is to perform the optimization. So geomechanical constraints can directly impact the optimization scheme. I will show in a few slides more. Simplicity and we have to make geomechanical solutions cost-effective as possible, And to do this, we are trying to use the simplification that we are proposing is the pseudo-coupling. Pseudo-coupling that we can, it was a result of a thesis that we just finished, that we can make pseudo-coupling give the same results as the two-way coupling. That's a more robust coupling, if you correctly update the tables of the geomechanical simulation. And for the optimization, we are going to use the sequential approximation optimization. That is one of the algorithms that we do very well in our group for well-controlled optimization. So this is the previous results that we had a few years ago that I just will highlight some elements of these results. So in this case, it was the Olympus model that we presented in other occasions, that we have about 1,440 controls rates in BHP. So it's a field that we have. So we generate 50 probable realization to account the petrophysical and uncertainties. And as each simulation is 45 minutes, this is too much for optimization. Optimization will call many times this reservoir simulation, so we are going to use 5 representative ranked realizations. And so you have 2 options in our group that we work, is the refined ensemble-based optimization method and also the sequential approximate approach optimization that is the one selected. So in this case, we define a trust region for the optimization in the optimization space that ensure the precision of the surrogate model. So you are going to use a more or less simple surrogate model, interpolation of the results of the based on the simulation, reservoir simulation. And by using the quadratic control of the trajectories, the number of nodes can be reduced to 54. And okay, in the assembly, it's another approach that we can generate approximate gradients of the objective functions by means of sensitivity analysis that reduce the spurious correlation and improve accuracy and so on. So the results that we obtained in the past with the sequential approximate optimization were better than the other options. So we are in this project, and the initial approach will be to use this sequential optimization, sequential approximation optimization. From the geomechanical point of view, what I would like to show is one of the results of a big project, a 5-year project that we finished this year with Petrobras. That is one of the results of the Raquel Oliveira Lima thesis that is concluded in these years as well. She was advised by myself and my colleague Leonardo Pereira at Petrobras. And the initial idea of the project is to decide, to create criteria to decide how important is geomechanics for that field. And how we can generalize this conclusion. Of course, it's very difficult, and we couldn't create this criteria. But we had during the process we had many achievements that I will mention to you. So the field is a field that was provided by Petrobras, all the data for the flow simulation and also for the geomechanics. And we build in our in-house geomechanical code, we build the geomechanical model to run with the SimG simulator. So, and this was a quite comprehensive study on geomechanics for this field. So the main objective, one of the objectives is to develop two-way partial coupling codes in terms of improve the development of two-way partial coupling codes in terms of CPU time. So we think that the idea that we had is at some point we are going to use this in optimization, in uncertainty quantification. So this is a demand of the industry. So, of course, evaluate the influence of porosity update. So we have many. mention in the next slide. So how porosity can be updated in geomechanical model. We have many options from the literature. The effect of geomechanical mesh discretization. And we perform a PCA, so a multivariable analysis to check the influence of the variables, the correlation of variables that impact the problem, the coupled fluid and deformation problem. And compare the results with coupled simulations with those conventional reservoir simulations. In this case, we create a way that we can, if you have the two-way coupling, we can build a pseudo-coupling simulation, and that will give us the same results. And if you want the final results in terms of geomechanics, we just have to run once the geomechanical code, put in the pressures that we came from in a one-way coupling scheme. So with this, I can mention some of the results. We test many ways to coupling geomechanics and flow simulation, and we could do this because we have a fully coupled code. That is our in-house code that can compare with the two-way coupling. So we found that this formulation that we are present here is the best. We get the best results. It's based on pseudo coupling. It's based in a pseudo compressive rock compressibility. And another investigation was to check the geomechanical mesh. It's not necessary to use the same or a coincident mesh with the flow mesh. We can use coarse meshes until a certain point. So we are not going to lose results in terms of pressures or displacements. So this is very important, because if you can use coarse mesh with adequate upscaling technique, you can really, for the geomechanics, we can really use more cheaper geomechanical model that can be used in optimization and uncertain quantifications. So also the coupling frequency of the two-way scheme. So it's not in a couple reservoir simulation with two codes, with flow simulation and also geomechanics. It's not necessary to run the geomechanical code at each time step, of course. And that this frequency is very important, because more I call the geomechanical code, more CPU time I would take for the complete simulation. So we also, in this case, we also evaluate some algorithms that will decide based on the pressure results or in the deformation, the frequency that we can call the reservoir simulator, and it depends on how fluids are. If you have gas, we have to call more times. So it depends on the classification of the reservoir. So. But at the end, we decide a final algorithm that gave us good results. We also study the depth of the reservoir. We consider, of course, for shallow reservoir, geomechanics is more important. It has higher impact. And also the oil properties of the. So it was give us many data, many very interesting insights on this, on all these aspects of coupled reservoir and simulation and geomechanics. And this was very interesting. The principal component analysis show us the correlation between the variables. I don't know if you can see, but you can see that, for instance, the stiffness of the cap rock and reservoir is inversely will affect inversely the production of oil, but it will have not very big influence on the gas production, for instance. So We have this correlation between the variables that are in a coupled simulation. And another important result is that only with two principal components we can describe very well the correlation between the variables. Also, if you add, we have a loose correlation here with pressure, but if you put three-dimensional, we can see completely that almost all we can describe almost all the variables using three components in the principal axis, principal variables. So we have insights from the optimization. So we are going to use sequential approximation optimization. We have some insights from geomechanics. We are going to use, for instance, or try to use the pseudo-coupling as a proxy or approximation for the fully coupled or the two-way geomechanics. So the objective of the project, putting together reservoir simulation and optimization and geomechanics, is to the implementation of management optimization tools that consider integration of geomechanical simulators with the conventional reservoir simulator and that allows the verification of geomechanical constraints related to stresses, deformations, and displacements. So we are interested in fault reactivation, compaction and subsidence, hydraulic fracture, and so on, to include this phenomena in the reservoir management, and also considering, and then the variables are the same. In this case, is production optimization. So all the considerations will be the variables for the optimization remain the well controlled, so rates and BHP. So for one side, we have two-way coupling. That is a more accurate, computational, very expensive, and pseudo coupling. That is less accurate and computational cheap, but and available in reservoir simulators. And the question is, can pseudo coupling replace the two-way scheme when executing optimization algorithms? And the answer is yes. We could prove this in the Raquel's thesis, that we can use pseudo coupling replacing two-way if you build correctly the tables, and sometimes we can have different tables during the geomechanical simulation and during the coupled simulation, but we can have almost the same results. And if you want the results in terms of geomechanics, we just have run once the geomechanical code in a one-way coupled coupling scheme. So we can put another layer of the optimization that is similar to the trust region approach. That is, we can define a trust region for the pseudo-coupling simulation in the geomechanical space of the variables, and we can update the pseudo-coupling tables by the two-way call. So we can use for a trust region, we can use that pseudo-coupling schemes for that set of tables, and then if you are far from this region, we can update the tables using a two-way coupling. So we have questions, of course. It's an approach that we are trying to work. So I would love to have recommendations and opinion, but by you all, and so we have questions. So size of trust region, the frequency of table of updates, and what the extent of geomechanical nonlinearities. Andrew, 6 minutes for my talk. Yeah? Okay. Oh. So we have to consider different types of variables in terms of effective stress and or strain. Depends on the operator, or depends on the engineer that is in charge of this management. So it can impact directly the the problem. So I have no more time, so I will skip the conclusions. I just put the final conclusion. That is, the proposed methodology can also be adapted for projects with underground and geological storage. Underground geological storage, of course, it will change the objective function, restrictions, and the variables optimal. The optimization problem will be different, but the approach that we are developing for how to couple with geomechanics, I think that we could adapt it for this kind of optimization. That's it. Thank you very much.
Thank you, Dr. Guimarães. We have time probably for a couple of questions, but there's one online to start with, actually two. How do you check convergence when you solve the transport equation, like finding pressure saturation, and then solve the geomechanics, like finding new porosity, permeability, and compressibility? So how do you solve the convergence, or check for convergence?
Yes, we have this algorithm that we run. If the pressure is when we run the flow the geomechanical simulation, and we have a very huge change of the pressure, it indicates that we have to update the porosity and permeability earlier than we did in the simulation. So you have to control this automatically with our algorithm. Yeah.
Okay. Second one is it fully implicit or consists of solving fluid flow implicitly and then geomechanics explicitly?
We can do fully implicit, but it's impossible. It's very, very expensive. So we do a two-way coupling. So we run explicitly, but exchange variables from between the simulators. I don't know if it is exactly the question, but yeah, this is the way.
Okay. There's nobody here yet. Okay. One question from one of our board members, Dr. Bob Gochner, is loose coupling, in addition to stability issues, typically incur or introduce material balance problems. Have you accounted for this?
Yes, we have to check this. The criteria is pressure, but also we can have, if you have how to say a huge how to say jump of the pressure, it is a sign that we have loss of material balance. So we have to be careful with the jump of pressures during the simulation when we update the porosity and permeability. And
as you mentioned, this process is automatic.
It's automatic.
If the pressure kind of exceeds a certain range and whatnot.
Exactly.
Right? Yeah. And that's my experience as well a long time ago when I was looking at coupling.
Exactly.
You know, as long as it's pretty steady, it's not much of a change, you can call the geomechanics, less frequently than a fully integrated approach. So that's pretty good. Thank you for that. Any further questions? If not, we thank Dr. Guimarães for your presentation again.
Thank you very much.